Hi students, today we are going to see the class 10, chapter 2, numbers and sequence. In sequence and numbers, here we are going to see the first equal division lemma. Here, the lemma is nothing but a mini statement or a mini theorem. Because it is a mini statement or a mini theorem. Let's go through the theorem. Let A and B, let A is greater than B, be any two positive integers. Here A and B are any two positive integers. Let me take it as A has one positive integer and B has another positive integer. Let it as 10 and 7. See, A is always greater than B. And then B any two positive integers means positive integer means we know that it is only the plus value from 1 to infinite, whatever may be the number, right? Then there exists a unique integer Q and R. Here Q is the quotient, R is the remainder. It has a unique integers, right? Such that A is equal to BQ plus R. It is the relation from A is equal to BQ plus R. Here 0 is less than or equal to R, less than B. Let's see how to write the given two integers in the form of equal division form. Let me take it as 10 as the dividend A. Let me take it as this is A, this is B, right? So 10 divided by 7. What do you get? 7 ones are 7. The remainder is 3. So this is the remainder. This is the quotient. Here it is the dividend. It is the divisor. Now compare with this. How to write the given terms? So A is equal to 10, and then B is nothing but the divisor 7. And then Q quotient is here, it is a 1 plus the remainder is 3. It is nothing but a remainder theorem. In remainder theorem we have studied in the 8th and 9th standard. Now compare this with the dividend is equal to divisor into quotient plus remainder, right? Now compare this. Always the biggest positive integer is the dividend, and then next digit, that is B, is the divisor, and then Q is the quotient and R is the remainder, right? Next we see the same format. We can write many other examples also. We can write the terms. Let me take this. The number 17 is divided by 5. See, 17 and 5 both are positive integers here, right? If suppose the 17 is divided by 5, 5 3s are 15, we get the remainder as 2. We may write this as in the form of equal division means, that is 17 is equal to, the divisor is 5, then the quotient is 3 plus the remainder is 2, right? And then same way we are going to see the equal division algorithm, right? Next we have the equal division algorithm. Here what is the difference between the equal division lemma and the algorithm means? Lemma we have distribute that A is equal to BQ plus R format. Here we are going to find out the highest common factor of the two positive integers or maybe two or more positive integers. In this algorithm means we are going to do the step by step method to find the highest common factor, right? Let's see that equal division lemma algorithm, right? Equal division algorithm. If A and B are positive integers, the same condition, A and B are positive integers. Let me take it as the same number, that is 17 and then 5. Last we have to take example sum. Here also we take the same number 17 and 5 such that A is equal to BQ plus R, then every common divisor of A and B is a common divisor of B and R. That is the A and B are two positive integers, Q and R are the quotient and remainder. The common divisor of A and B is also a common divisor of B and R, and vice versa. What the number is divisible of, the common divisor of B and R is common divisor of A and B is the meaning of vice versa, right? Now compare this. 17 is divided by 5. 17 is divided by 5 means, what is the quotient here we have? 17 is divided by 5 means 5 3s are 15, remainder 2. So 5 into 3 plus 2 is the remainder. Here, when we are doing the algorithm means we have to continue the steps up to the remainders is equal to 0. Up to the terms, remainders remains equal to 0, right? Then here the remainder is not equal to 0. That is 2 is not equal to 0, right? Then we have the terms. I take the 5 to this side. The divisor became a dividend. So 5 is equal to. Then the remainder became a divisor. Then the remainders became a divisor. Here I took 2. Now we have to divide the term. 5 is divided by 2. We get 2 2s are 4. Remainder is 1. So 2 into 2 plus 1. Here again the remainder is not equal to 0. Remainder is not equal to 0. We are going to the next step, right? Up to how many steps we have to do? The remainders become 0, right? Next we have to take the divisor to this side. That is 2 is equal to. Then here the remainder is 1. 2 is divided by 1. Take that number. 2 is divided by 1. 1 2s are 2. We get the remainder 0, right? So 1 into 2 plus 0. Here the remainders become 0. So the number 17 and 5, the highest common factor is HCF of highest common factor is that is 1. HCF of 17 and 5 is 1. See, we have taken the 17 and 5 as AB, right? Next we have see that B and R. See here R is nothing but 0, right? Here our remainder is equal to 0, and then the divisor B is equal to 1. We have the highest common factor of both the terms. That is the division algorithm. We go through the step by step up to the remainders equal to 0. The HCF of A and B, A is 17, B is 5, and then remainder R is equal to 2, right? So the HCF of A and B is highest common factor is 1, and also the common divisor of B and R. See here B is 5 and the remainder R is 2 is also the common divisor is 1, right? Thank you students. Hi students. Today we are going to see the exercise number 2.1 in chapter 2. The question number 1, find all positive integers. Find all the positive integers when divided by 3 leaves the remainder as 2. By using the Euclid division lemma, we are going to find the positive numbers, right? By Euclid division lemma, you know the formula, right? That is A is equal to B cube plus R is the Euclid division lemma, right? Here, when divided by 3, here division is given and then remainder is given. We know that B is the divisor and R is the remainder, right? Here we want to find out what is the positive integers of A. So A is equal to, in the place of B is divided by 3. 3 cube plus the remainder is 2. Here I take the terms. We want to find what is the positive integer of A. See, A minus 2 is equal to 3 cube. See, in the term A minus 2 should be divided by 3. That is the actual meaning, right? So here A minus 2, I take the multiple of 3. A minus 2 is the multiple of 3 means first we take the 0 and then multiple of 3 is 3, 6, 9, 12 and it goes on. Now here we can be able to find out what is the A value. First I select this 2, that is A minus 2 is equal to 0 means then A is equal to we get 2. And in second term A minus 2 is equal to 3 means we get A is equal to 3 plus 2, A is equal to 5. See, here when A is equal to 5, in the place of A is equal to 5 is divided by 3. 5 is divided by 3. 3 ones are 3. We get the remainder as 2. So we have find out the positive values. That is, the first number is 2, second number is 5. By this we can be able to find out the terms. Another term is 6. That is, a minus 2 is equal to 6. Then a is equal to, I take this 2 to other side, we get 8. Add the two numbers in the each and every term. Therefore, the positive integers are what are the positive integers? 2, 5, 8, and it goes on, right? 2, 5, 8, and the next term, here it is a 9, 9 plus 2 is 11, and it goes on the terms. This is the positive integers of the number divisible by 3. Hi students, today we are going to see the exercise number 2.1, question number 4. When the positive integer a, B, C, here we have 3 integers, right, are divided by number 13, or divided by number 13. The respective remainders are 9, 7 and 10. Show that A plus B plus C is divisible by 13. The integer A, B, C is divisible by 13. We get the remainder as 9, 7 and 10. Right? Solution. By Euclid division lemma, we know the formula, that is by Euclid division lemma, we have the form A is equal to BQ plus R. That is the form, right? Here it is general form. So now the integer is given as ABC. So the A is divided by 13. We get the remainder as 9. So A is equal to the divided by 13 quotient Q, and then the remainder is 9 for the first one, right? Let me take it as equation number 1, and then second integer we take it as B, also divided by 13. We get the remainder as 7. So here B is divided by 13. We get the remainder as 7. Take the equation number as 2. Next, the third integer, that is C. C is divided by 13. We get the remainder as 10. Now we want to show that sum of the 3 integers, right? That is A plus B plus C. So here we are going to add all the 3. Then only we get A, B, C. Adding equation number 1, 2, and then 3. See, if you are adding that, the LHS should be added separately. That is, LHS we have A, B, C, right? If you add this term, we get A plus B plus C is equal to. Now we have add the RHS side. See, in the RHS side, if you add this term, we get 13 plus 13 is 26. 26 plus 13 is 39Q plus 9 plus 7 is 16. 16 plus 10 is 26. And then this term is equal to, see, both the numbers are divisible by 13. So I take commonly 13 outside. So we get 3Q plus 2. Now this term is equal to A plus B plus C is the multiple of number 13. Multiple of 13 means A plus B plus C is always divided by 13. Therefore, A plus B plus C is divisible of 13. Today we are going to see the exercise number 2.1, question number 6. Use Euclid division algorithm to find the highest common factor of, right? By using the division algorithm, we want to find out the highest common factor of this. First common number is given as 2 integer. See the positive integer 340 and 412 by Euclid's division algorithm. We have the form, that is A is equal to BQ plus R. And then see the two integers that is given as 340 and 412. We know that here A is always greater than B. The dividend is always greater than the divisor. So we take it as 412 as A. 412 is equal to, the divisor is 340. Now we want to find out the quotient and remainder. See, here 412 is divided by 340 means it will be clearly only one times, right? 1 into 340 is 340. When you subtract this, we get 2. More 11. 11 minus 4 is 7. So 1 plus 72. See, the remainder is not equal to 0. Up to the step should be followed, the remainder turns to 0, right? So clearly this article is not equal to 0. Next we have to change the divisor as a dividend. Take this down and then the remainder as the divisor. So now 340 is, there is a step by step method, right? And 340 is divided by 72. How many times it possible means? Here we have 7, 7 5s are 35. There is no 350, right? So we get possible of 4 times. Then 4 2s are 8 remainder, and then 4 7s are 28. When we subtract this down, we get 10 minus 8 is 2, and then remainder here 3, borrow 1, 13 minus 8 is equal to 5. So still the remainder is not equal to 0. 72 into 4 plus 52. Still the remainder is not equal to 0, and then have the another step, that is 72 is divided by 52. Now take the 72 as this here and then divide by 52. It is only one times, right? We get 52 ones are 52 and then remainder is 0. Still the remainder is not equal to 0. See, 52 into 1 plus 20. The next step you have to move the divisor into a dividend, that is 52, and the remainder as the divisor. In 52, how many times is possible? Divided by 20 means we get clearly 2 times, right? 2 into 20 is 40, we get remainder as 12. So still it is not equal to 0. Here we have 12. Then move the next step. The divisor is turned to the dividend, and then remainder turns to the divisor. Now 20 is divided by 12. Clearly it is a one time, right? 20 is divided by 12 means 12 ones are 12. We get 8 as the remainder. So plus 8. Next I take the 12 here is equal to 8 as a divisor. So 12 is divided by 8 means 8 ones are 8. The remainder is 4 plus 4. Next I take the 8 here and then divided by 4. Clearly 4 2s are, right? 4 2s are 8. Now here you get the remainder as 0. 4 2s are 8. The remainder is 0. Here, when which step you get the remainder as 0, that particular divisor is the highest common factor of these two positive numbers, right? So therefore, the HCF of highest common factor of 340 and 412 is 4. By step-by-step method, this is the way to have to find the highest common factor by using Euclid division algorithm. Okay, let's see the second common number. Here we have the second common number as 867 and 255 is the second common number. By using the Euclid division algorithm, here we have a is equal to bq plus r form. So the greatest integer is 867 is divided by 255. Now you want to find the quotient and remainder. 867 is divided by 255. Now see, compare the two digits here. Here 25 into 3 is 75. So less than this number, right? So we get 3 times if possible. So 3 5s are 15, 5 remainder 1. 3 5s are 15 plus 1 16, 6 remainder 1. 3 2s are 6 plus 1 is 7. Now subtract the term, we get 2, 6 minus 6 0, and here we have 1. So quotient is 3 and the remainder is 1 or 2. See, the remainder is not equal to 0. Next we have another step. 255. I take the divisor will be a dividend and then remainder will be a divisor. That is 1 or 2. Now 255 is divided by 1 or 2. Now compare the two digit, right? Here 10 twos are 20. So less than this number. So we get 2 times. 2 into 2, 4, 0 and then 2 not 4, right? Then separate the term, we get 1, 5. 51. How many times? It can be again 2 times plus 51. See, again the remainder is not equal to 0. Now we go to the next step. I take this 1 or 2 as dividend and 51 as a divisor into 1 or 2 is divided by 51. How many times? It is clearly 2 times. That is, we get the remainder as 0. So 51 into 2 is 1 or 2. So we get the remainder as 0. When we get the remainder as 0, that place we have the divisor. The divisor is the highest common factor of these two given positive integer. Therefore, the HCF of 867 and 255 is highest common factor is 51. So when we get the remainder as 0, that steps divisor is equal to the highest common factor of this two positive integers. Thank you, students. Hi students, second chapter, numbers and sequence, exercise number 2.2, we are going to see the question number 4. If 1, 3, 8 to 4 is equal to 2 power a into 3 power b, then find the a and b. See, here 2 and 3 are the prime numbers. We want to find the power of these two prime numbers, right? By using either a factor tree method or a prime factorization method, we can able to find out the value of what is a and b. That is 1, 3, 8 to 4 is equal to 2 power a into 3 power b. Now, by using the simple prime factorization method, we can able to find the value of this. That is 1, 3, 8, 2, 4. By using the prime number, the last number is an even number, right? 4 is a even number, so it is divisible by 2. If it is divisible by 2 means 2 6 are 12, remainder 1, 18, 2 9s are, right? And then 2 1s are, 2 2s are. Still it has a even number, so divided by 2, we get 2 3s are 6, here we have 2 4s are 8, remainder 1, so 11, 2 5s are 10, remainder 1, 12, 2 6 are 12. Then again it is an even number divided by 2. We get 3, 1 2s are 2, remainder 1 is 14, 7 times, right? And then 2 we have, here we have 5, 2 2s are 4, remainder 1, 16 means 8s are, 2 8s are, right? Again divided by 2, we get in 17 we have 8 times, right? 8 2s are 16, remainder 1, 12 means 6 and then 4. Divide by 2 again. 4 2s are 8, 4 3 2s are 6 and then 2 2s are 4. Again divide by 2, we get 2 2s are 4, here 2 1s are 2, remainder 1, here we have 6. Again divide by 2, in 2 we have only 1 times, in 1 it is not possible, so put 0, and then 16 we have 8. Divide by 2, 108 is divided by 2 means we get 54. Then 54 is divided by 2, we get 27. 27 is a odd number, so it is not able to possible to divide by 2. So we get the next prime number is 3. 3 9s are 27, and then 3 3s are 3 1s are. So these are the prime factors. Now here we have how many times of 2 we have seen? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this term is equal to 2 power 9 into 1, 2, 3, 3 power 3. Now this term is equal to 2a into 3 power b. So let me take this 2a into 3 power b. In the place of a we have the number 9. In the place of b we have the number 3. Therefore a is equal to 9, b is equal to 3 is the answer. Students, exercise number 2.2, question number 5. If p1 power x1 into p2 power x2 into p3 power x3 into p4 power x power 4 is equal to 1, 1, 3, 4, 0, 0 is given, where here p1, p2, p3, p4 are primes in ascending order, and x1, x2, x3, x4 are integers. Find the values of p1, p2, p3, p4, and also we want to find the value of x1, x2, x3 and x4. We want to find the prime numbers and then integers there. So the given term is 1, 1, 3, 4, 4, right? Solution 1, 1, 3, 4, 0, 0 is equal to, we want to find the prime numbers, that is p1 power x1 into p2 power x2 into p3 power x3 into p4 power x power 4. By using the simple prime factorization method, we can be able to find the value of the prime numbers and integers. Here I take the, by using the prime factorization 1, 1, 3, 4, 0, 0. So it is a clearly even number, right? So it is divided by 2. Suppose it is divided by 2. What I get? 2 5s are 10, remainder 1, 13, right? 2 6 are 12, remainder 1, 14. 2 7s are, and then 0, 0. Again it is a even number, divided by 2. We get 2 2s are 4, remainder 1, 16. 2 8s are 16. Here we have 7, 2 3s are 6, remainder 1, 10, 2 5s are, and then 1 0. Again divided by 2, 2 1s are 2, 2 4s are 8, 2 1s are 2, remainder 1, here 15, 2 7s are 14, remainder 1, 10, 2 5s are. See, the last number is an odd number, here it is not possible to divide by 2. Next we take the number 3, the prime numbers, right? So 3 4s are 12, 3 4s are 12, remainder 2, so 21, right? 3 7s are 21, here we have 7, 3 2s are 6, remainder 1, 15, 3 5s are 15. Next, divide by 3 again, 3 1s are 3, remainder 1, 17, 3 5s are 15, remainder 2, 22, next term, right? 22 means 3 7s are 21, remainder 1, then we have 15, 3 5s are 15. Again divide by 3, here 3 5s are 15, 3 2s are 6, remainder 1, 15 means 3 5s are. Again divide by 3, we get 3 1s are 3, remainder 2, 22 means 3 7s are 21, remainder 1, 15, 3 5s are. Right? Again, divide by 5. It is not possible to divide by 3. Right? 3 5s are 15 and remainder 2, 25. 25 is not divisible by 3, so we take it as a number 5. See, 5 3s are 15. 5 3s are 15, remainder 2. 25 means 5 5s are 25. Again divide by 5, we get number 5 7s are 35. 7, right? And then 7 1s are 7. So completely we have found out. So these are the prime numbers. 2, 3, 5, 7 are the prime numbers. Here P1, P2, P3 are the prime numbers, and then power x1, x2, x3 are the integers, right? So we have the arranged in an ascending order. So this term can be written in the form of 2 into 3 into 5 into 7. So only we have 2, 3, 5, 7 only, right? Now we have to find out the powers of times it appears 3. 2 is appearing 3 times. 1, 2, 3. That is 2 power 3. And then 3 we have 1, 2, 3, 4. So 3 power 4. 5 we have 2 times. And then 7 element 1. So here the 2, 3, 5, 7 are the prime numbers. The value of P1, P2, P3 and P4. Here P1 is equal to 2, P2 is equal to 3, P3 is equal to 4, P4 is equal to, sorry, here we have 5, right? P3 is equal to 5, P4 is equal to 7 are the prime numbers. Now the integers are the powers are the integers x1, x2, x3, right? These are the integers. Then x1 is equal to 3, x2 is equal to 4, x3 is equal to 2. And then x4 is equal to 1. So here we have the P1, P2, P3 value and then the integer x1, x2, x3